Today I'd like to make a few more comments about some historical development so we kind of have an appreciation for where this field is going. And then I'll spend a little bit of time talking about some other statistical issues, mostly for fun. I don't have all of the TA assignments together yet, but I do know who the TAs are going to be. Robert Buckley, who handled most of the labs this past week, Carolina Elva, and Kevin Angelou will be the TAs for the course. And I will let you know probably next time which sections everybody is covering so you know who to talk to. Last time, I believe Robert briefly summarized some information from the salary survey. We put this up just to get some idea about where the solid state circuits area, which is the integrated circuit design field, sits. And this is the 2016 IEEE salary survey data. And the median salary for engineers in that field, what's that number? For solid state circuits? 165,000, that's the median annual salary. And if you scan up and down the other areas, you'll notice that that's pretty much the top of the salary structure. In fact, there's a lot of difference between one part of our discipline and another. Robert talked a little bit about yield. We had something called hard yield, and we lose devices when we fabricate them because of what happens on a wafer. What do we get on a wafer? What? We get defects. We have the die on the wafer, but defects tend to occur due to dust, typically, or other particles that are associated with the processing of the silicon. And these particles are really small, these dust particles. But if a dust particle was 1 micron in diameter, and your device dimensions were a tenth of a micron or smaller, that dust particle might wipe out a whole bunch of circuits. Or consequently, a dust particle as small as the size of a transistor, or a fraction of the size of the transistor, could cause failure of a circuit as well. So the hard yield, for the purpose of this course, we're going to assume it's e to the minus AD, where A is the area of your die, and D is the defect density. And what we see then is that for a small die area, the yield is very nearly 100%. But for a large die area, the yield goes to very nearly 0. So there's some unfavorable trade-offs between yield and area, and that puts a fundamental limit on how big our areas can be in a die. The reason I'm going to stop with this model is, first of all, that's not our goal in this course, to try to real accurately predict yield characteristics or fault models. This is close enough that this tells you about what's going to be going on. If you're in an industry, they will probably have a slightly different model, same general characteristics, but they'll closely guard what the parameters are in that model. Why do you think industry typically closely guards what their model is and what the parameters are in their model for yield?
Because if you know someone, you can know it's better.
Because what?
You can know it's better.
You can know a lot about your competitor's part. In fact, it's not uncommon to have one company that has a lower defect rate than another company. And if that's the case, they know what it's going to cost their competitor to make a part. It could be the case that you make your competitor lose money by pricing your components such that you make a profit and you can guarantee they won't make a profit. So they're really sensitive to protecting this kind of information. We also saw that there's another way we lose die, and that's due to what we call soft faults. And a soft fault is due to a continuous variation in parameters between devices that are closely placed. So we'll talk about something called the threshold voltage of a transistor a little bit later, but the threshold voltage is the voltage which allows the transistor to turn on. And if you put transistors ideally identical on an IC, some will turn on at a little bit lower voltage than another would. And the turn on voltage becomes a random variable. And if you're building things like an op amp, and you've talked about op amps in 230, offset voltage is one of the key parameters of an op amp. Offset voltage is almost always determined by mismatches in devices. And if the mismatch is too big, you can't sell the part because the part goes out of spec. Customers just don't want a part that has a large offset. So that gives rise to what's called soft faults. The device is still functional, it just doesn't meet the performance requirements that you're interested in. Could happen in digital circuits too. Could be that the speed of a particular processor is not quite as fast as another one on the same die due to random variations in characteristics of devices. The one that operates faster is probably worth more than the one that operates slower. And indeed, a lot of times they will sell those faster parts as premium parts, or those slower parts, they'll discount the price on those. They come off on the same wafer at wafer sort. They're just graded differently. The overall yield is the product of the hard yield and the soft yield. Usually they're uncorrelated, so we can multiply the two yields together. And then we talked about the cost per good die. So if you start losing some die, you can calculate how much it costs to fabricate a die by looking at the cost for the wafer and the number of die on the wafer and taking that ratio, and that's what it costs to fabricate a die. But when you have to throw some away, then your cost per good die goes up. So your cost per good die is the cost for fabricating the die divided by the yield that you have for making those parts. And so that was the equation that you should have looked at last time. Do you guys like statistics? How many people like statistics? One, a couple like this, the rest. How many people don't like statistics? Wow. What have we done to convince so many people to not like statistics?
You can take a statistics class.
Yeah, maybe. So you came to Iowa State. I'll bet everybody that raised their hand that says they don't like statistics wouldn't have raised their hand when you came in the door for the first day of class as a freshman. And so something happened between the time that you arrived on campus and you're sitting in this classroom today. And you develop a lack of appreciation for statistics. Maybe because we make you take a statistics course. Maybe that's the reason. Or maybe there's some other reasons as well. Something must be oozing out of these walls that convinces people that statistics are bad. You know, what happens in much of what we design in regard to what it's going to cost us to make it is governed by statistics. And you can either ignore statistics and let happen what will happen, or you can understand statistics and know what's going to happen. If I'm a designer, I'd like to know what's going to happen. I'd not like to wait until after we get in the marketplace and we find we're losing money on a product. Your boss is not very happy about that situation, and probably you aren't either. Of course, you might be surprised the other direction and say, wow, this device has a great yield, much better than I expected. That's really a rush, right? Will your boss be impressed if you have a part that has a much better yield than you expected? Well, be careful, because that usually comes at a cost. The enhanced yield is likely due to you put too much area into the circuit. And more area means more cost. So if you have a part that's got a much better yield than you expected, because you didn't do your statistical calculations, and you go in and tell your boss, wow, look at this great yield I got. It's much more than I expected. And your boss says, you know, you could have sold a part for 50 cents. And you spent 70 cents on fabricating. Take the area back out and get the yield down to a place where we make more money. So will you impress your boss if you have more yield than you want? The answer is no, because you put too many resources in your product to get it out the door. How will you know what you really should do? Look at the statistics behind it. Does that make sense? Okay, so I really hope that we can leave this class with the understanding that statistics are real. They really govern what's going on. Statistics really are your friend. And this feeling that statistics are something that we don't like and don't want to work with and so forth, try to work hard to dispel that. Try to work hard to say, hey, now I really need to understand what the statistics are associated with a particular design. You'll be much better off. We're not making you take that statistics course to punish you. You're asked to take a statistics course because it brings really useful concepts to designers. If we fail, I think we fail in pointing out what the relevance is of a course like that. You talk about feature size. Feature size is typically the minimum features that we can make on a process, and it's usually the minimum width of a metal run, or the minimum length of a transistor, or the minimum width of a transistor, and so forth. And they're usually about the same. We'll talk about cases where they might be a little bit different. But we have the feature size determined by how small it can be so that we can reliably make a circuit. So if you have a circuit that has 50 billion transistors on it, how many of those transistors do we want to have good? How many of them do we want to be good? All of them, all 50 billion transistors. And if you look at those transistors, when you consider the interconnects and the contacts and so forth, there's probably at least 500 billion features that need to get put together to make that circuit. If any one of those features fails, that circuit's not going to be good. So it's going to be reliable if all 50 billion of those features are going to be good, with a high probability. High probability that all 50 billion features are good. Okay, so we can cheat on a circuit pretty easily and scale dimensions down. You can take a 22 nanometer process, and if you go in and squeeze the features down to 20 nanometers, a lot of circuits will still work, but a lot of it wouldn't be as reliable. So we set the feature size so that we can expect to have billions of features being good in that process. Makes sense? Doesn't mean you can't make one device or a small number of devices at a much smaller feature size, and part of them will work. It means a high percentage of them are going to work if you work with the feature size that's specified. Robert talked about the transistor. The MOS transistor was discovered in 1925 and 1935, 10 years apart. Pretty much a worthless discovery. Why was it pretty much worthless?
Couldn't make it.
Couldn't make it. If you can't make it, what good is it? 1947, the BJT was conceived. That was an important discovery. Why was it important? Because they made it. Not only did they invent the device, they were able to build the device, and that's what got Silicon Valley going. Was Shockley a good physicist? Yeah, he was a brilliant physicist. Was he a popular individual? No, he had some real rough edges around him, both in his personality and his beliefs. And it really tarnished, I think, the contributions that he made to our profession. In 1959, Jack Kilby and Bob Noyce invented the integrated circuit. Kilby was a little bit sooner. Noyce had a little bit better design. We spent the better part of a decade trying to decide who we should give credit for developing or inventing the integrated circuit. And in the end, we said, well, they were co-inventors of the integrated circuit. So here's a picture of an integrated circuit. On the left, you'll see the die, and on the right, you'll see that die embedded in some package, a lot of times plastic, with some leads coming out. Here was Kilby's patent. It was filed in February of 1959. Took 5 years from the simple patent application to get approved and awarded as a patent. That's a long time. Thank you very much. And if you look at the circuit that he put together, it's kind of similar to what we're going to be talking about in this course. And what he didn't have, so he had the idea that he could put more than one transistor on a piece of silicon. That's why he called it integrated. But he didn't have a good way to do the interconnects. So you see some wires interconnecting the devices together on silicon. Here's a picture of Jack. I'll tell a story about Jack. I'm probably only standing here because of Jack Kilby. I was at another institution a number of years ago, and the department chairman came by. I was a young assistant professor at the time. Hair wasn't gray or bald. And the department chairman came in and says, I'm looking for people to put together an integrated circuit program. Any volunteers? And when you do this, you kind of get involved with it. And anyway, Jack worked at Texas Instruments at the time, and Texas Instruments and Texas A&M, where I was at, decided that it would be good for the industry to have an IC design program. So Jack was the catalyst for making that program happen. And he came to campus every 3 weeks for several years to provide oversight in regard to putting the program together. He was a brilliant individual. When I walked in the first day Jack Kilby was there, I didn't know that he invented the IC. I heard that there was this important person by the name of Jack Kilby that was there. I walked in about 8 o'clock in the morning, and I saw a guy walking down the hallway with a yellow and white shirt, kind of a stoop walk, and Jack was a big guy, and I thought we'd hire a new janitor. Walked in the room to discuss the program, and that janitor sat down at the table and provided guidance in regard to what's going on. So that was Jack Kilby. One characteristic that Jack had, he was incredibly immersed in how the world around him operated. So he made multiple inventions. One was the integrated circuit, which is pretty significant. Also the handheld calculator. He was an inventor of the handheld calculator as well. I think that there's a couple other people that have parts of the handheld calculator, but he was a major part of the handheld calculator. But it didn't seem to make any difference what kind of discussion one got into. Jack was knowledgeable about what was going on, whether it's device physics or electronics or opera or whatever the case might be. He really immersed himself in society to try to understand what went on, and I think that helped him be a very, very productive inventor. Here's a picture of his original integrated circuit. It sure looks like a mess, doesn't it? Those wires glued on or stuck on somehow to demonstrate that it worked. Here's Bob Noyce. Where did Bob Noyce come from? Grinnell in Iowa, down the road about 60 miles or something. And here was his patent. If you look at a cross-section of this, you'll see that's very similar to what we look at today. But the thing about Bob Noyce is that he had figured out how to do the interconnects as well. So he didn't have to put extra wires on to do the interconnects. Bob Noyce was referred to as the mayor of Silicon Valley, and he really played a key role in the evolution of the semiconductor industry there. Shockley decided to go there to build transistors. Noyce and Moore were the ones that really turned that area into a thriving group of companies that put the area on the map. Something else that's interesting to observe is the age of these individuals when they made these inventions. Jack Kilby was 34 and Bob Noyce was 31. what you'll see is a lot of the major innovations that take place in many fields, but certainly in the microelectronics field, happens to people that are very early in their career. So as you're sitting here right now and you get some idea, don't discount it too much. I mean, it may well be the idea that really makes things happen in a year or 2 or 3. In 1971, Intel introduced the 4004, and it was the first microprocessor. It was a 4-bit microprocessor and a 10-micron process. 10 micron feature sizes on the transistors. And what sizes do we have now? 10 nanometers are common, right? What's the difference in feature size between 10 nanometers and 10 microns? A factor of 1,000 in lateral dimensions. What's the factor difference in area? 1,000 squared, which is 1,000,000. So transistors today take out about 1/1,000,000th of the area the transistors took in 1971 when Intel introduced the 4004. At that time, they had 2,300 transistors. If you scale that by 1,000,000, what does that come out to be? About 2 billion. So we've scaled more than the area ratio since that time. Oh, what I spent a little bit of time talking about statistics. We had somebody giving a lecture here a number of years ago talking about either Six Sigma or T2M or something. And I asked the person, he was a VP at a major semiconductor company. I said, what if people don't buy on to the idea? And without hesitation, we fire them. So there's this mentality that we have Six Sigma or else in the industry. So let me talk about the Six Sigma challenge. How many people have heard about Six Sigma designs? Six Sigma designs? Yeah. And where'd you hear about it at?
I mean, I've heard Six Sigma just from my mom. That's going through some sort of Six Sigma training at Wells Fargo.
Okay, Wells Fargo. Somebody else? Where'd you hear about it?
John Deere.
John Deere. They're in the Six Sigma. Okay. Where else? Who else? What?
Just manufacturing.
Manufacturing in general. You know, if you go back to the early 80s, we were having a real problem with products that were manufactured in the United States. Whether it be washing machines or automobiles or electronic components, we needed repairmen. We needed return policies. We were expecting lots of failures to occur. It was just the way things were happening. And the Japanese were putting out products that did not have that same problem. So we started to try to address the question, how can we improve the quality of our products and get something comparable to what the Japanese have? So if you look at what the or else situation was then, you're fired. You either buy into this Six Sigma approach, which is going to try to allow us to compete with the Japanese on improving reliability, or you're gone. So let's see what Six Sigma really meant and where it came from. So here I show a Gaussian distribution. How many people have been through the STAT course already? How many people haven't, right? Anybody have? Okay, so several people haven't taken 333. Is that the STAT course? Pardon?
It's 322.
322, excuse me, 322. You've probably all looked at the bell curve before, even if you haven't been through the STAT course. Yield at the Six Sigma level, and they assume a Gaussian distribution, is equal to the area under the bell curve between plus 6 sigma and minus 6 sigma. 6 sigma is the standard deviation. So it's the area in blue there relative to the total area. Of course, the total area under the bell curve is 1. So if you want to look that value up, it's twice the cumulative distribution function at the limit, since it's symmetric, twice the cumulative distribution at 6 minus 1. And you'll find that yield is 0.9999, a whole bunch of more 9s than an 8. So if you have 6 sigma performance, it's really good. The yield is really high. The Japanese didn't have 6 sigma type performance. We were going to be much better. It's approximately 2 defects out of 1 billion parts. 2 defects out of 1 billion parts. So how many smartphones are sold in a year in the world? 1.5 billion? Okay. That's close. I thought it was around 500 million, but we're close. So around 1 billion, somewhere between 500 million and 1.5 billion smartphones a year. So if you had this type of a yield on your smartphone, that means that around the world, all the phones that are sold, on the average, you have about 1 a year that would not work. Are we that good? Not even close. Not even close. That's an incredibly high. That's an incredibly high yield. If you're at 5 sigma, it's 1 part out of 5.7 million. If you're at 4 sigma, so that's not as good of a yield, you're at about 63 out of 1 million and so forth. So here's the 6 sigma number that we just looked at, 2 parts in 1 billion. Now, when the concept was initially introduced, it was assumed that performance or yield will drop for some reason after you get the manufacturing process going by about 1.5 sigma. So they expected, and this is really a weird assumption because we're going to see where it came from in a bit. In the semiconductor industry, if you get a certain defect density or yield today, you're going to expect the requirements to get more stringent a year from now. The argument is, as your process matures, you should have better yields. But they made the assumption that for some reason, things are going to relax out a little bit, and you'll start out at 6 sigma, but you'll end up with 4.5 sigma performance, which corresponds to about 3.5 defects in 1 million. That's still a very small defect rate. Okay? So that's the mathematics behind the original 6 sigma approach. So it's a highly statistical concept. So this picture kind of shows what goes on. That initially we start on the short-term capability of 2 parts in 1 billion, but when things get a little bit sloppier over time, we can slip to about 6.8 parts in 1 million. So let me look at an example. Determine the maximum die area if a circuit yield is to initially meet the 6 sigma challenge for hard yield defects. I'm going to assume a defect density of 1 per square centimeter, which is a very good defect density, and only hard yield loss. Okay, so we're going to work backwards now. We're going to say if we want to have 6 sigma yield, how big can we make the area of our die? Because we make it bigger, the yield goes down because of the defect, right? I'm going to do this calculation to get some idea about how realistic it would be for somebody to come in and tell you you must design your circuits to meet 6 sigma characteristics. Any guess at how big that die area is going to be? What? Big. We'd like it as big as possible, right? We'd like it as big as possible. So the yield is twice the cumulative distribution at 6 minus 1. So the yield is e to the minus AD. So we can take the natural log of that function. We find the area is minus the natural log of the yield divided by the defect density. And the area that we have then for Six Sigma performance is going to be 2.5 E-fifth, so 250,000 square angstroms. A die area of 250,000 square. Is that a big die? Well, we're not usually looking at square angstroms. It would be an area equivalent to that yellow box there, 500 angstroms by 500 angstroms. And of course, you have to have bounding areas around it, so maybe it's somewhere around 20 angstroms on it. I said that back. I said that wrong. If you look at a minimum size transistor, in a 20 nanometer process, it will have a lateral dimension of 200 angstroms. So this is compared to the area required to fabricate a single transistor in a 20 nanometer process. Okay. So we're going to get 6 sigma yield on our ICs. We can put one transistor in. Is 6 sigma performance too stringent? You're trying to make engineers design circuits with 6 sigma performance, it's an easy task. What can you do with one transistor and that's it? Right? Wow. So, you kind of got to be quiet about telling somebody that we're not going to make 6 sigma performance on our designs, because it's not going to happen. So is it realistically, well, let's jump up. Let's jump ahead and just observe that arbitrarily setting a 6 sigma performance standard will guarantee financial disaster. Can't make anything. So if we can't make 6 sigma performance, what can we get? We'll find that improving the yield even by 1 sigma is challenging. So if you have a design done, and somebody comes in and says, well, let's go from 3 sigma to 2 sigma. That's a big amount of effort. I'm sorry, from 2 sigma to 3 sigma. It's a big amount of effort to improve the yield by one standard deviation. So this is an example of where statistics can be abused. In fact, the fallacy on this is that we've assumed that what's important is a standard deviation. What's really important is what our profit is on a part. So if we focus on optimizing a standard deviation, we will get some design done. But there's no guarantee that that design will optimize financial return on your design. So what should we be focusing on? Doing design that optimizes the financial return on your product. Make sense? And that has nothing to do with artificially setting up a certain standard deviation requirement on the engineers. So this is a case where statistics can be abused. Many that are not knowledgeable incorrectly use statistics. And a significant number of Fortune 500 companies are committed to the 6 sigma challenge. The 6 sigma approach to improving reliability of manufactured products is an honorable concept. But oftentimes statistics are intentionally used to mislead the public. Look at all the polls that you see that come out where you're not told what the questions are. A hypothesis test is going on, but you're not told what the hypothesis test is and so forth. But yet you're having the press or other people interpret the results for you. So that's a situation where where statistics maybe are being intentionally misled, are used to intentionally mislead the public. Some openly abuse statistics for financial gain or manipulation. So I think it's really important to keep an open mind to separate good statistics, which really tell us what's going to happen when we design systems, from bad statistics where people are either unknowledgeable about what's going on or use them in a way that tends to mislead society. Make sense? So let's see how the Six Sigma approach materialized. Motorola was the leader of that. I recall going down to Motorola when I used to be at Texas A&M, and their microprocessors used to be made in Oak Ridge facility in Austin. I recall going into the lobby of this beautiful Motorola facility. It was a 3 or 4 story lobby, and they had a banner on the top of the lobby in letters that were taller than me, totally committed to the Six Sigma Challenge. So there's no question about the fact that Motorola was pushing this. Motorola was a multinational telecommunication company in Schaumburg, headquartered in Schaumburg, Illinois, which eventually divided into 2 independent public companies, Motorola Mobility and Motorola Solutions, in January 2011, after losing $4.3 billion from 2007 to 2009. So if a company loses a couple $1 billion a year, is that a big deal? Well, if you look at the size of companies like this, we talked about the annual sales of TI, $10 or $12 billion, and Marvell, $5 billion, and so forth. When a company's losing a couple $1 billion a year, that's a big issue. Motorola was an American company. So let's see how Motorola fared with the Six Sigma approach. So if you look for the ticker number for Motorola, you'll find that, what's it say? It was founded in 1928. It was one of the most successful companies in the United States for many years. But it says defunct in January 2011. That's not a good sign to see. So here's kind of their history. They sold their military activities to General Dynamics in 2000 and 2001. They sold their automotive products in 2006 before they lost their several $1 billion the next couple of years. They spun off their discrete semiconductor components as ON Semiconductors in 1999. They spun off the semiconductor products sector, which is where they made most of their ICs, as Freescale in 2003. It was acquired by NXP in 2015. They sold Motorola Mobility to Google in 2011. Google in turn sold it to Lenovo in 2014. Motorola Solutions now has 16,000 employees. It's down from 150,000 they had in the mid-1990s, about the time they were doing this work. Wow. Motorola has really changed, hasn't it? The Motorola saga continues. Qualcomm, remember NXP was semiconductor product sector. Semiconductor product sector, I thought, had 40 or 50,000 people. It was a major manufacturer of ICs in the 80s and the 90s. And NXP was the new name that the old Philips of Europe morphed into. And Philips was a major competitor of Motorola. They were doing everything electronics throughout Europe, a really major company. NXP, which acquired semiconductor product sector from Motorola, was going to purchase NXP. Qualcomm was going to purchase NXP, and this was dated October 27th, 2016, a little less than 2 years ago. I was visiting people at NXP at the time who had been with Motorola previously and then with Freescale, and they were in the process of laying off people and redesigning their focus so that when this merger was complete, they would be aligned with Qualcomm's interests. Trump blocks Broadcom bid for Qualcomm. Oh, another company comes in there. Broadcom is another company that was a U.S. company that got acquired by Avago, and they decided they were going to acquire Qualcomm. And of course, then we have this Motorola being part of the Broadcom, Qualcomm, I guess the Broadcom operation. And this was dated May of 2018. So now some issues are starting to crop up because Freescale's in the process of, NXP's in the process of being incorporated into Qualcomm. All of a sudden, Qualcomm has some big changes in plans because their merger with Broadcom got blocked. And, in May of 16, a little bit later, they were talking about Qualcomm's purchase of NXP. Some questions arose as to whether there might be some problems cropping up. And then in June of this year, the Chinese approved Qualcomm's purchase of NXP. That's not very long ago, is it? July, a little over 2 months ago, a little less than 2 months ago. And then on July 26th, the whole thing fell through. Qualcomm drops the NXP acquisition, and I don't know where things are heading right now. And this is less than a month ago. So the saga of what happened to Motorola and where those people are at continues to change. So, meeting the Six Sigma else, did it serve Motorola well? Well, we certainly can't blame the demise on Motorola on their Six Sigma approach. But had they religiously tried to do exactly what they proposed, they would have disappeared, as has happened. I'm certainly not going to blame the Six Sigma approach that came out of Motorola on their demise. I think they did some good things in the process, but they abused statistics. Six Sigma capability has almost nothing to do with optimizing profits, and if taken seriously will likely guarantee a financial fiasco in most manufacturing operations. So, what do you do when the top people in your organization say Six Sigma or else, and or else is you're fired? At the time that Motorola was promoting that Six Sigma approach, I would go in and visit with some of the engineers, and I'd ask them if they were going to meet those requirements. And it became clear that they didn't even understand, some of them I talked at, didn't even understand the statistics behind what the banner in the lobby was saying. So, Six Sigma or else? Well, you mentioned John Deere, a company that's promoting Six Sigma performance, and I don't know, something like 2/3 of the Fortune 500 companies are doing something similar. The concept of improving reliability or really profitability is really good. And I think that most of these programs that are called Six Sigma programs, they dispense with the statistics. They use the name and focus on trying to make the company more profitable by cutting down defects at the right level. So the concept's fine. It's just the statistics are somewhat abused. So hopefully we get the message as to what's expected with Six Sigma challenges. So here's the perception. The earnings per die or the earnings per product would go up as the yield variance gets higher and higher. As we go from 3 Sigma to 4 Sigma to 5 Sigma to 6 Sigma, the assumption is that we become more profitable. And that's probably what motivated the Six Sigma approach. Realistically, if you look at the earnings per die as a function of the yield variance, you'll find that it always looks like this. So Six Sigma is almost always underwater. But notice that for a viable product, there will be a certain variance that will maximize the earnings per die. And my premise is, as an engineer, you need to set your variance requirements so that you're at the peak of this curve. How about yield? I almost got escorted out of a company a number of years ago when I made the comment that 100% yield should not be your target. So there's also perception that you want to have yield close to 100%. The higher the yield is, the more profit you'll make. The idea is you don't want to throw away die that are defective. Well, if you look at the cost per good die, it almost always will have a curve like this. So there's a big pressure to improve the yield, because for a fairly wide yield range of many products, improving the yield will improve the profitability. It'll reduce the cost per good die. But as that yield starts to approach 100%, the cost per good die will turn around and get really high. So we can look at it at our goal for yield in a different way. And that goal should be to set the yield at a level that will minimize the cost per good die. Yes?
How has this curve changed over the last 3 years?
This is just an artist's drawing. It's been in the same general shape all along. So the only change is where that inflection point is going to be at. And it may be the case that for some products that inflection point is 10%. And other products that inflection point might be at 99.9%. So it can went very wildly from product to product as to where that minimum cost of good die is. But keep in mind, throwing away good die, if you can cut the cost per good die, throwing away die, if you cut the cost per good die, is something you really want to do. So let me close then with the comment that the designer's goal should be to optimize profit, not to try to arbitrarily optimize some particular yield target. Does anybody have any questions? Is Six Sigma good? The concept is good. The statistics might be some trouble. That's all we did.